All right, everybody, this is the beginning of chapter 17 and 18, which we do together, which is all about water, the aqueous systems we find, and the solutions that we make. So we're really going to delve into a lot of things that we have seen from other chapters. All right, so first things first, let's talk about water. Water is H2O. And if we remember back to our molecular bonding chapter, oxygen has 6 valence electrons, so it has 2 lone pairs. Hydrogen has 1 valence electron. Everybody wants to obey the octet rule, so we end up seeing that the molecular composition of water looks exactly like this. It has 2 lone pairs, so there's no bonding here. The bond shape is bent or angular. It has a bond angle of 104.5 degrees with its 2 lone pairs. So this little bent shape that we see here is going to give water some very special properties. And that is something called polarity. So like poles of a magnet, poles of the earth, okay, a polarized person with bipolar disorder, they have 2 sides. They have a positive and a negative side. So if we remember back to the electronegativity chapter that we had, electronegativity is the tendency of an atom to attract another atom or an electron when it's already bonded to something else. Okay, the electronegativity is going to decrease as we get down here towards francium, and it's going to increase over here as we get towards fluorine. Well, oxygen is over here, and we end up having hydrogen over here. So oxygen is going to be more negative, and hydrogen is going to be more positive. This little sign that you see here is called delta. Okay, so the lowercase letter delta is going to mean partial. All right, and partial means that part of the water molecule is going to be positive, part of it is going to be negative. So if we have our molecule here, like so, all right, the partial positive is over here, partial positive is over here, partial negative is over here. The Greek letter delta has a capital delta, like we have a capital D, and the Greek letter delta kind of looks like a little bit of a cobra, a weird little S. That is like our lowercase d. So the Greek alphabet has the same uppercase and lowercase letters that we do. The capital D delta means change, and the lower d delta means partial. So this part is positive, so the positive part is like right about here, and this part is the negative part. So just like a magnet, just like a pole, just like anything else with 2 sides, we end up seeing this is the positive part, this is the negative part. So when water does this, we see that it is actually going to charge and pull things apart. It's going to add to a bunch of different special characteristics that are very unique to water. And because like over 70% of our planet is made up of water, this is going to mean that we're going to see lots of things that normally doesn't happen with liquids with our water. So the special characteristics that we're going to look at is something called surface tension. We're going to look at its density as a solid, meaning when it's ice, and then the special dissolving properties, which is what the rest of the chapter is. Okay, because we're talking about the solutions and the different systems that it has. All right, so first, surface tension. Okay, that is the tension on the top of the surface of water. If you have ever belly flopped when it is nice out and you have been swimming, you know all about surface tension. Okay, divers have to dive straight into the water and not onto the water flopping down, because if their belly hits the whole thing, ouch, it is going to hurt. These little water skipper bugs, they spread out their body weight all the way out here to take out this really big area on their 6 legs so that they don't sink. All right, so surface tension is going to be those positive and negatively charged atoms of water that are going to kind of hold and make like a skin to the surface of the water. All right, and that skin is going to have stuff float on it. All right, so if these are little water molecules in here, you can see that each one is going to have a positive and a negative and a positive and a negative and a positive and a negative that are all going to attract to one another, and they're going to make these really cool little droplets. All right, and these droplets are going to what give our earth and all the matter, all of the celestial bodies in space, that nice spherical shape. Okay, so when people say that the earth isn't round and it is in a sphere and it's flat, I'm just like shaking my head because it's absolutely impossible. All right, I attached videos that you see in class on how astronauts drink in space. You can end up seeing that water has a perfect sphere right here, and it's so cool. I think this would be one of the coolest things in the entire world to experience. Would be basically like Pac-Manning water. And then here's another instance with them using a wet washcloth in space and seeing how they end up wringing it out and the surface tension along with that. Okay, in class I do a little demo with some water, and I take a paper clip and I can float it on the surface. Even though it is metal, it spreads out its weight. That's basically how, boats work. And then you can take a paper clip and put it straight up and down, and it breaks through the surface tension of the water. And then I add soap, and soap works by breaking the surface tension. Okay, so if it breaks the surface tension, that's how we get nice and clean. Okay, because it breaks up all the surface tension of all the different bacteria and viruses and stuff like that that's going around. So wash your hands. It really, really works. All right, we do a little mini lab in class also where you take a penny and you count the number of drops of water that you can fill on top of it. It creates this very nice dome and looks really cool. And then we take the same penny, but then we use soapy water, and then we see what the difference is. And then we can talk about what soap does to the surface tension and kind of prove again how awesome it is to wash your hands. All right, the second criteria for the properties of water is the density of solid ice. Okay, so water has a density of 1 gram per milliliter. So a milliliter or a cubic centimeter is going to weigh 1 gram, but ice is going to be 0.92. So ice floats. There are over 4 million different kinds of compounds in the universe. And in nature, none of them do what water does. None are less dense as a solid naturally than water. There's a couple of elements that do it, but they don't exist in nature naturally. So what happens is when the water molecules freeze, they have to get into a very specific formation. Here you see the negative part. That has to align with the positive part of this water molecule. And this positive or this negative part has to align with this positive part right here. And they have to get into formation, just like Beyonce says, in a very, very special way. Okay, when they're water, they're all like, woo, I'm gonna flow all over and splash and bump off and spin and woo, all over. But as a solid, they have to get in a very specific spot. That's why ice expands. All right, and that's why we see ice floats. So when it expands, it gets into those very specific rigid formations where the water molecules have to align in a certain way so that the excuse me, the negative and the positive and the negative and the positive and the negative and the positive and the negatives and the positives all align up in a very specific way. Like I said, gallium and bismuth and germanium do this. They're not common by themselves. They're always in some sort of compound in nature. But water's the only one that does that. And it makes these little tetrahedral holes where this is empty space. So the water expands. If you put water in an ice cube tray, okay, in your freezer and fill it up to the very edge, when it freezes, it actually comes up above it. That's why we get potholes and all those crazy things here in the Philly suburbs. Okay, so ice will float. It will be less dense. And good thing that happens. Good thing that that happens, because if it didn't, how in the world would life exist? Life is going to survive regardless of whether it's summer or winter. Okay, life exists in a pond in the Arctic or anything like that, and things wouldn't have evolved if it weren't for this. So here you have your water molecules, which are going to be solid as ice, and it has a density of 0.92 grams per milliliter. And here you have your water, which is 1. So fishy still can fish, and our seals can still go around, and ice algae and different fish and jellyfish can still live and not die. Because if not, and the ice would come under and on the bottom, none of this stuff would be able to eat, and it would be very sad. No aquatic life, which means all the things on land that hunt the aquatic life would not be around, and the things that hunt those wouldn't be around, and so on down the food chain. So these exceptions that water does is very, very important.